All right, today we're going to look at 8.4. It's the comparison test. So far, everything we've been doing is does it converge or diverge? Basically, true, false. And we've had several tests so far we're looking at. We're going to add two more today in 8.4, two more different ways to compare. Um, One is just direct comparison, and the other one is limit comparison. So we're going to jump in and look at those kind of examples. The key to this is the fact that you want to choose, let's say, less than or equal to b sub n. So 0 is less than or equal to a sub n is less than or equal to b sub n. Now I'm going to choose, I may know a series, I'm going to call it a sub n. And I'm going to choose a b sub n to compare it to. The thought process here is if b sub n converges, if it's going towards a number, then a sub n must also converge, because it can't jump over b sub n and all of a sudden go off to infinity. So if b sub n is heading towards a number, then a sub n must be at least heading towards that number, if not a number smaller. So if I can compare, if I know that b sub n converges, that tells me that a sub n must converge. Very similarly, if I am starting off with b sub n and I would compare it to an a sub n, if I know that, now I'm going to talk about what happens if I know that a sub n is, if this one's divergent. In other words, this one is heading off towards infinity. Well, if this is going off to infinity and it's less than b sub n, then b sub n must also be going off to infinity, and therefore it's divergent. So I can tell two things with the comparison test. One, if I know b sub n is converging, then a sub n must be convergent too. Or if I know a sub n is divergent, then b sub n must be divergent. Let me point out what we don't know. All right, if a sub n ends up being divergent, I'm sorry, if a sub n ends up being convergent, in other words, this one is heading to some number, it tells me nothing about b sub n, because this could be heading to a number or it could be going off to infinity. I would never know. So sometimes the comparison test isn't going to tell you what you need to know. Likewise, if this one is divergent, it's going off to infinity. A sub n can be going off to infinity, or it can be going to some number. We just don't know. So you got to choose what you're comparing carefully. Well, that was a lot of information without any solid examples. So let's see what I'm talking about. So as an example, let's look at the series n equals 1 to infinity, 1 over 2 plus 3 to the n. Well, that doesn't follow any of our geometric p-series, any tests that we have so far. So we're going to try to compare it. I'm going to choose something to compare it to. Often to choose is looking for the highest ordered term. In other words, if it's the polynomial, look for the highest order there, or if it's an exponential, look for that. So I'm going to compare this to, I'm going to choose to compare it to 1 over 3 to the n. Now let's talk about what I know about this series. 1 over 3 to the n is the same as that. So I think you know that indeed converges, because it's geometric and it has a ratio with an absolute value less than 1. So this one we know for a fact converges. Let's put them in the order that they should go. 1 over 2 plus 3 to the n is indeed less than 1 over 3 to the n. And you have to think of it this way. If I'm dividing by a number larger than this, then that's obviously going to be smaller. For instance, let's just use if this is 1 over 100, and I add 2 to this one, then clearly 1 over 102 is going to be less than 1 over 100. If I'm dividing by a larger number, in this case larger by 2, then for sure it's less, slightly less, but less nonetheless. So now let's look at how to set this up. Well, I should have just left that. So we have 1 over 2 plus 3 to the n is indeed less than 1 over 3 to the n. And we know for a fact that this is converging. Now, because this one's less than that, if this is heading the number, there's no way this one can jump over that number to get to infinity, so therefore this one's converging too. So I can reach this conclusion by comparison test that the original series was converging. Let's look at another example. I'm going to choose, this is the summation as n goes from 1 to infinity of 1 over 2 plus square root of n. I'm going to compare it to 1 over square root of n. Now that is the same as 1 over n to the 1/2. And you know by the p-series that because that number, that exponent is less than 1, that indeed this thing is going to diverge. We learned that on a p-series test, so I know it's divergent. But the same argument we just made, 1 over 2 plus square root of n is clearly less than 1 over square root of n. 1 over square root of n is divergent. All of a sudden, I realize, well, this is going off to infinity. This could be going to a number. It could be going to infinity. I don't know. So that did not work. Was not a good thing to compare it to. Let's try to compare to the harmonic 1 over n. Because we know, we've seen several by p-series and or integral tests, that this is indeed divergent. But now let's put them in order. 1 over n is less than 1 over 2 plus square root of n. Why is that? Well, clearly n is always going to be a bigger number than 2 plus the square root of n. And so, or at least for larger n, we're talking about as n goes to infinity, that's a true statement. So if that is true and we got it in the right order, this is divergent. If this one's going off to infinity and it's smaller than this one, then this one certainly is going to infinity as well. And so now we can draw the conclusion that that sequence was divergent. That's called the comparison test, direct comparison test. We also have a limit comparison test. A limit comparison test says the limit as n approaches infinity, a over n to b to n is equal to some L. So I am going to use a sequence and I'm going to compare it to something. I'm going to divide them and find the limit as n goes to infinity. This test says if L is basically a number, but if it's finite and positive. In other words, if L is a positive number, then what we can draw the conclusion that whatever was happening with the one I compared it to is happening to the one that I had to start with. In other words, if A sub n was convergent, then B sub n is also convergent. Or, sorry about that. Or if A sub n is divergent, then B sub n is also divergent. All right, so let's see an example. I think that'll get you guys less confused about this. I'm going to look at the series as n goes from 1 to infinity, 1 over n plus 3. Now, by the way, we could use direct comparison on this. I would compare it to the harmonic, perhaps, and do that. But let's look at it as limit comparison. I am going to compare this to the harmonic 1 over n. So I'm comparing it to this series here. The one you're comparing it to is always the one that's on bottom. So I'm looking at the limit as n approaches infinity of the original 1 over n plus 3, and I'm dividing that by the one I'm comparing to 1 over n. Well, dividing by a fraction is the same as multiplying by the reciprocal, so that's talking about the limit as n approaches infinity of n over n plus 3, which you know is heading to 1. Because this is a number, it's not infinity, and it's a positive number. It's a positive number, then that tells me whatever was happening with the one I compared it to is happening with the original one. We know 1 over n is divergent, so it means that this one is also divergent. Kind of a neat, clean little test. But If had this one we compared to been convergent, then this would have been convergent. But we know the harmonic series is divergent, so this is divergent. Let's look at another example. The summation as n goes from 1 to infinity of the square root of n over n squared plus 1. What am I going to compare it to? I'm going to compare this to, or I'm going to compare this one to, you look at the leading coefficient. So I'm going to look at that over that. The square root of n, which is n to the 1/2, over n squared. So you choose your comparison based on the leading term of both things. Now when I reduce this one, it is 1 over n to the 3/2 on bottom. So that's basically what I'm comparing it to. So we have the limit as n approaches infinity of, actually, I think this one might work out neater not to reduce this one. We're going to leave it like this. So we have the one on top, square root of n over n squared plus 1, divided by square root of n over n squared. And you can see why I didn't want to reduce it now. Dividing by the fraction is the same as multiplying by the reciprocal. So this is square root of n over n squared plus 1 times n squared over square root of n. These cancel out. I'm evaluating the limit as n approaches infinity of n squared over n squared plus 1. Once again, 1, they don't all work out to 1, but in this case, these two did. That is a positive number, which is what we're looking for. So it says if that comes out to be a positive number, whatever was going on with the one I compared it to is also happening with the one I started with. Now we know by p-series, and that's where it helped to reduce this one. We know by p-series that this one here is convergent because that p is greater than 1. So if that one's convergent, then by direct comparison, this one must be convergent as well. All right, we're going to see one more example. Let's look at the summation as n goes from 1 to infinity of n over 2n over 4n cubed plus 1. I'm going to compare that to, looking at the leading terms, n times 2 to the n. This is times, that's not raised. I don't have on the same level, but n times 2 to the n over 4n cubed, just looking at those leading terms. Well, I am going to reduce this one because that n will cancel out with n on bottom, 2 to the n over 4n cubed. Or I'm sorry, n squared, because that n cancels out with that. So what do we know about this one? Well, let's talk about it. This one is just squaring a number. This is an exponential function. Exponential functions increase way faster than polynomial functions. In other words, we're going to have a much bigger number on top divided by a smaller number on bottom. It's going off to infinity. I can confidently say this one is divergent. So we're going to use our limit comparison test. The limit as n approaches infinity of the original one, 2, n times 2 to the n over 4n cubed plus 1, divided by the new one. Dividing by any fraction, same as multiplying by the reciprocal. I'm going to use the unreduced one to do that. 4n cubed over n over 2n. You can see why I did that. These are going to cancel out. Look at the limit as n approaches infinity of 4n cubed over 4n cubed plus 1. Again, this is heading to 1. It is a positive number. So whatever's happening with this one is happening with this one. This one is divergent, so this one is divergent. All right, that's a lot to absorb. You guys are going to have some homework to practice. I'll come around and help you out if you need it. Thank you.